Hi everyone, my name is Pavel, and we have unfortunately Needy is was a bit sick, so we have Thiru here coming in to join us, and he'll be contributing as well with the presentation. But thank you all for joining. We're going to learn a little bit more about on-chain AI inferencing, specifically targeted towards developers. Yeah, I guess right now let's just jump right into it. So let me share my screen right now. And yeah, we'll go in with like a brief presentation, then we'll do some code review, and then we will bring it to Thiru to actually demonstrate this. And Thiru, again, if there's any questions or if anything, feel free to interrupt and ask away. Hopefully, this will be like a learning experience for everyone. So, on-chain inference, AI inferencing for devs. So, AI agents are essentially the large language model is the vehicle. It's the infrastructure that performs the requests. The data is the navigation system, tells the actual driver or the agent where to go and what to do, or like what data to inference off of. And then the agent itself is the driver. So it uses that LLM, it uses that backend to perform an action. So what we want to do is we're taking these different types of parts, and we want to bring it into a more transparent and verifiable system. So with traditional AI or AI that we see today, we don't really know this information. We don't know if the model ran correctly. We don't know if the model was retaining or going and using some form of data that we might have requested. We don't know if the data was tampered with. We also one of the big problems is when relying on these systems for these interactions, we don't really know if these can be trusted for financial-based operations. There's tons of the ability to essentially change things, make it a very high-risk type of way to do these different types of interactions. We essentially through LazAI want to create a verifiable AI marketplace. So essentially registering data on chain, allowing for jobs to be created and cryptographically verified that the data that was inserted is correct, and essentially giving people the ability to earn rewards off of inserting data, but also for the providers to verifiably use that data within their applications. And then also the next layer is to get those providers to transparently process that interaction as well. So the whole life cycle is what we are accomplishing with this. So looking at the LazAI client, hopefully people are familiar with Aleth. Aleth is the overall client that does this, the interactions, let's say like the framework for making AI agents. The LazAI client actually sits underneath Aleth, and essentially it handles the more so of the on-chain interactions. And it does these interactions to the Hyperion blockchain, but also to the LazAI blockchain, which will be coming out as well. And then with that, jobs are requested from different nodes, and then those jobs are the ones that actually run those inference operations or the data validation operations. So the LazAI client is like a banking app. So it allows it essentially abstracts the complexity behind it, registers data on chain. It requests computation for different actions like inference or verification of files. And then it also manages the payment infrastructure. So the goal is that you will be able to make these types of interactions all through this type of unified system. So let's run through some brief code examples on the different types of steps within the lifecycle. Of course, these are not all the steps, and this is not all the code. I'll actually demonstrate some examples, or I'll show some code to some examples where you get to see this more so in action. So the first is depositing to a node. You would essentially specify the specific node that you are requesting, essentially the inference-based operations. And this one, you would essentially have to pre-seed or pre-fund your account to basically make those interactions for. Then afterwards, you would register your data. And this data essentially is verified within that specific structure where the nodes are essentially coming in and verifying that the data does in fact exist. They can generate proofs that that data is present, and then you would of course have some form of a monetization aspect on providing that trained data for this. And like this, what I highlighted was essentially the token amount that you want to spend in order to run this. And then for the actual secure computation, you would essentially run a server, make requests to this to a external node, and that external node would get information about who is requesting, and making sure that things like nonces, signatures, making sure that it's that user that is requesting that data, and associating it to that node that did that request. So making everything more transparent, verifiable, what exact life cycle essentially operations have happened, and using these forms of verification. So what we see here as a deposit for like a data registration, let's say. So you are calling a add file function to the LazAI client, and then this essentially sends a transaction to the blockchain, which registers the file ID. And then as a result, that file is returned back, or that file ID is returned back as registered. So looking into the smart contract functionality, we have the data registry and anchoring. This is essentially the catalog that you are using to pull the data for use. Then we have the AI process. So this is for managing the different types of jobs that the AI that the nodes will be doing. So some of the jobs like data verification and inferencing are done via this process. Then we have the settlement layer, where essentially it distributes the payments, make sure that your account balances that are associated with the action that you're trying to do is aligned. And so, as mentioned, the pre-deposits, this pre-deposit structure would essentially allocate the rewards based on the specific parameters of what the marketplace is looking at. So if you have like maybe higher complexity operations, or the data that needs to be more thoroughly verified, maybe there's an increased cost for that. So there's also IDAOs and proxies. And so an IDAO is essentially just an organization that controls some form of a data subset. So they can, it's an organization, they decide what the overall, like how everything is managed and maintained, and they have essentially ownership and access rights to the data as well. So and then of course like managing maintenance upgrades. So this is more of like the governance layer for that. So we have the data registry, where we're able to add a file, create a on-chain record of that. Now, of course, the data isn't present on-chain, but you would be able to use an IPFS hash to essentially pinpoint where that data is. And since it's IPFS, more of the what is it, the request is done for the data that's actually not a URL where the data can be changed, but the where that data is, what that data represents, rather than where that data is. So of course you can use a regular URL, non-IPFS, but of course when we're talking about like where that data is, can it be accessed, the IPFS is probably one of the primary ways to store permanent data. Now the ability to verify the node, verify that data is when that function of add proof, and so that add proof specifies the ID that the add file operation was given, and then the proof is essentially that the verification that went into that process to make sure that that data does in fact exist and is accessible. And so the final way is that upon providing the data, you would essentially get a DAT, or data anchoring token, and that corresponds to the ownership of that asset and potential royalties that come with it. So next is we have the AI process contract, which is the essentially for every type of work, for every type of operation, whether it be inference, training, or querying the different types of resources, it comes to the AI process contract. And so it has its own worker nodes and sub-accounts as well associated with it. So if you can think of it as like a wide web where people are able to assign their own workers, the cost of which, and then like what, and then making sure that your account doesn't get debited, your master account doesn't get debited for something that for a operation that gets done by one AI agent when should have been done by someone else. And so essentially the concept of these sub accounts, making sure that any operations are not are encapsulated to their own entities essentially. So the nodes themselves are running off chain, and then they're submitting on chain as a proof. And so the contract itself verifies it and then distributes payments after verification. And then the actual function to distribute the fees are also in here. So when a node completes a job and then gets paid for that job being completed. And then the settlement layer is actually a lot of these intertwine. So I guess the previous AI process and settlement sort of combined, but essentially the goal for this is that the payments are actually distributed on this specific contract, and so it knows where to forward to the correct AI process. So that's where it is intertwined. And so essentially when the payment, or when the process or the work is done, whether it be the AI data verification or the actual inferencing, that gets finalized on the settlement contract. And so finally, IDAO and proxies. So the IDAOs, they're essentially whatever kind of governance operation. It could be a single entity. It can be multiple different people managing like a multi-sig. They're the ones that are the maintainers of the data repositories. And so essentially, the goal of this is of course the longevity. So that's why we have proxies. So you're able to upgrade for different types of features that would get released depending on what data registry there is. So this is an overall sequence diagram of how someone would use this service. So when the client requests proof, that is when you're depositing a file. When you're trying to verify a specific file, you make that request, and then you can also make a inference off of that with using a specific node that you've assigned to make that inference request. And so after that, the system allocates the funds, which in this case adds an account associated with the user ID that you've provided, and then with a specific node that is associated with it. So essentially, you're saying that this node is responsible for that AI inference operation. And then so that creates the actual account for the user that then can be debited. And so you would send this inference request using that server method that we showed previously. And then afterwards, when it reaches that node, so again, like going way back right here, you would send an inference request specifically to that node, and then go in and that node processes that data. It would then submit the on-chain verification of it, so it settles the payment. Then the node gets some amount of rewards for doing that, and the user's balance is deducted from that. So this when you first add in the balance, the AI model runs it, does some computation, receives payment for that on-chain settlement, and then the user also gets their balance deducted. With this, the key takeaways is that we wanted to create this as a easy to use way to make this type of interactions possible. So we've prioritized 3 languages primarily: Rust, Python, and JavaScript, to make these inference requests. And then so the actual inferencing itself is done by the with the data validation proofs. So every single data source that gets added has to be accompanied with a proof that that data is valid. So, and that it was verified by a specific node that was likely assigned by the IDAO. So in this way, you have a view of the data that is essentially added to this source, and then as a result, the data registry is responsible for that. Let's say that contract that relates the actual data to the node who verified it. And as a result, the modularity of the system, we can add more features and functionalities without breaking it because of the proxy contracts. And then finally, why we built all of this, to that aspect of decentralization from the payments side for incentivizing operations to the actual incentivizing computational operations, as well as the data that gets submitted, and also the making sure that that's actually all parts of the supply chain are all adjusted for. So it's not just one node doing one thing, and you pay that one node to do one thing. You have the ability to distribute payments to multiple different processes for that specialized inferencing needs. Before we go through the demo, I want to see if we have any questions of anyone that's listening.
Actually, we have like no questions.
Okay, so I guess everything makes perfect sense. Got it. Okay.
Yeah, everything is clear. Yeah.
Yeah. So, well, in that case, maybe I'll blow your minds and go and look at the actual code behind this. Just very briefly, nothing too let's say time consuming, but all of this is present. Let me again share my screen. All of this itself is present on the Aleth repository. So that, like, if you go to 0x LazAI, I guess we can post that in the chat on that. But essentially, actually, let me.
Yep, I'm posting it. Don't worry.
Oh, perfect. Okay, perfect. Okay, so in that case, Thiru will post it, and then the contract itself are also on 0x LazAI, and as a result, they're not present on the Metis protocol docs, or not the docs, sorry, but the GitHub repository. So might be we'll definitely make that navigation a bit clearer when referring it back to our own documentation. So without explaining further, So I'll go through a little bit of these examples. The first is the data contribution. So with it, there are, of course, Python examples, but there's also examples in, so there's examples in Python, but there's also examples within Node. So Node examples, although I think there's like less of these examples present, but there's also examples in Rust as well. Actually, no examples in Rust. Could be. I guess we're there. The dev team is still working on those examples, prioritizing Python because likely it's the easiest one to go over. But at least, with the Python examples, we can see like clearly what exactly the intention of these are. So there's a URL that you can supply. So this is when we're doing the adding in the file for the data registration. And as a result of this, we can request a proof, and this goes into the overall client that the Python library is using. So within it, we have this is the LazAI client, where we are attaching the different types of contract methods here. And then for that specific one, sorry, let me we're going to the request proof. And this request proof, we have the file ID associated with it. We would go to the contract side, and we can take a look at request proof for the verified computing. And then as a result, we can see that when I am supplying the file ID, I can tell a node to essentially process this as a job. Once the job is processed, I would call the complete job function and as a node, and then I would receive the bit amount for that job that I have completed. So in this case, adding data to the specific repository for inferencing purposes. So going back, yeah, we can see like this get job. We can see the node that gets the job. We see that the proof request is submitted for the node, and you can do this as well with encrypted data. And then it makes a post request to the to the actual node itself, and generates the code or like submits to the actual to the actual contract, and then requests a reward from this, and the user can request a reward for uploading that specific file and be able to mint a specific DA token. So essentially that whole process just outlined adding in that file, it being processed by the node as a job, a proof being submitted to the contract, and then the user getting rewarded for submitting that data. Going through some other examples, if we go back to our examples here, we can see an inference request being made when a user essentially processes or like adds in their account balance for that specific node. So this is a node. They add in a specific balance to that node to be able for processing to occur. And then that request is made to the server. And the server has a port 8000. It has a specific model that it would do the inference off of. Or actually, this is the query server. Never mind. Let me just maybe like bring that up a little bit. So this is the query server. There's also the inference server. So this is the one that would be responsible for all of the settlement. But essentially, it makes a request here. It has specific token billing middleware, which is essentially the tokens that are, well, when an inferencing is done, you want to charge the user for the specific amount. Sorry, I think I went like a little bit diverted from what I was initially explaining, but like for the on-chain settlement part, we have the inference settlement, and then we're able to settle and collect the fees. So if we go over here, then to the verified computing contract, we can see that that the inference was done for that specific user, making sure that that user did in fact request that inference, and that balance has been present. And then assuming everything checks out, it will deduct those balances and then actually settle that cost associated with that inference. So the payment that the user made to this is all resolved in the AI process contract. Now, for what I was initially explaining with this, we can get the headers that the client is requesting, and then make that settlement request happen within this. So this is the one where we don't have a API or like it doesn't actually get called by the API. Then we have a request where it actually has that API call. So hopefully that doesn't confuse people. But if anything, you can review the code as well if you do have any confusions, or ask me if you need any clarification. But you would specify the file that you would want the node to inference. So want the specific node to inference, and then prompt that that node with the specific request that you're making. Yeah, I guess everything else, has its own example. So there's ones where we can add a node to the I believe to the specific to the network, the one that does the actual like data verification. There's some examples with I think I already went with this one, storing the data. There's one with managing access permissions to the data. So let's say it's sensitive data. You only want like a specific node to access it, or anyone with a specific key. And then, yeah, there's some related to like query examples. So in here we have we can go to the query server, and we're able to essentially pull a specific file from the registry. So if we go over here, we can see like, okay, there's a contract function get file. And then if we go over here, we can get the file, and that corresponds to the hash and the URL. So that returns the different types of parameters of that. So yeah, I guess like, do we have any questions or anything with that? Of course, like this is probably a lot to take in with like the level of examples and smart contract code and everything, but yeah. In terms of I know we're running a hyperhack bounty, so this is quite new in terms of the code that was added. But definitely, this is the goal that we're trying to achieve. It have this transparent AI inferencing with this way of making these requests. We want the hyperhack developers to focus more on the architectural portion. Of course, like if you're able to get it to work with the smart contracts and everything, that's above and beyond. But what we primarily want is that everyone understands the concepts, everyone understands the architecture behind these the different types of requests that are being made, right? If you understand this, if you understand how data registrations would work, how all of these processes are working together, then essentially building these together, building these components is much easier as a result. So for the hyperhack specifically, we want you to come up with a architectural diagram showcasing how you would implement this type of on-chain AI inferencing. Maybe not the data registration flow, maybe that's not what you're doing, but maybe you want to incorporate that job request, which then pays out based on specific parameters that are requested. So I'll leave it at that. I think Thiru, you have like a brief demo that you wanna showcase.
Sure. And then it's a good thing, like I think everyone get it because we have like no questions in the comment. So
Yeah,
yeah.
that's always a good sign, or maybe not.
Yeah. Yeah, for the demo, to give a like a quick context on it. So we're gonna definitely go through the data provider workflow. So how you can actually provide your data, and then some part of inferencing, and also like I'll also go through a few other examples. So without further ado, let's start. So I'll start with the data contribution flow. So we have the doc as well. So in the alike docs, we have the data contributed flow, like each and every step on Rust, Python, and Node.js. In this demo, we're gonna see the Node.js workflow, how you can set it up and then provide your data. And the result of this is you'll be receiving a DAT, which is a ERC 1155 NFT. And so we're gonna start from like setting up to getting the DAT, but I have already set up. But to give you a quick context, basically create in Node server, and so you don't need like Express and everything. You just need a basic a TS file. So in order to run TS, you need like TypeScript and all, and then install the npm package alert. I've given the index to a TS. We can take over from there. So here we have the index.ts which have the code. So we have added alert and node. So Axios, these are just like a helpful functions. So Axios to make the API call. And apart from that, what is required is the private key as well as the JWT. So both requirements are mentioned within the docs as well. I will post a doc link uh, in the live streams. So first, you can see the IPFS instance is created, and this is the crux. So your encrypted data file. So this is just a demo file that I have. So this file is supposed to have your encrypted privacy data that you are providing in order to receive the DAT, the data you are contributing to the network. So here, the private data is in the file, and so we have provided a private key as well, so which will create the wallet instance. And so we have our IPFS JWT. So this I've used Pinata. So I have to provide the JWT because the data is being stored in the IPFS. And so the client instance is created, and then clients add the file that we have provided. And so we will request a proof. So these are all the abstraction of what Pavel taken us through like few minutes back. So client instant is created, a job ID is created. So once the job is done, so we can see the like the public key and the URL of the node. So once that is done, so we encrypt the data. So this is the proof of request that we do, and we will get that in the JSON. So I'm just like writing it down in like a proof request JSON. We can take a look at it after we uh, run this file code, and we are using the Axios to call the node URL and with the endpoint proof to receive the proof. So if the status is 200, it is successful, else it is failed. And for the request, we need to have the file ID. So whenever we contribute, So the file ID will iterate. So you can see like whenever the last time I tried it is 72 and then now it is 73. Now if we do like it could be 74. So uh, for the package.json, it is basic. All these code is available in the doc. You can just copy paste, and we also have a user interface template that you can just like clone from the repo. I will take you through that as well. And so if I run npm run start, it basically runs the index.ts file. So what happens behind the screen? As I mentioned, the file is being encrypted using our private key, and it makes a transaction where the file ID is being stored in IPFS, as well as it is also make a transaction in last AI chain, and that stores the job completed in the last AI chain. So we can also check that in the block explorer. So I have received my file ID, which is 74, and I also take you through the proof request. So what we get in proof request is the file ID, the job ID as well. So file ID is unique to the data that we are contributing. Job ID is unique to the executed job in the node. And we have the file URL, which contains the data that we are contributed. Here's our encryption key and inscription seed. So we don't have a nonce and proof URL. So these will be populated on the upcoming steps when we receive a reward and then for the other features. So this is so within these like few lines of code, you could able to contribute your data, and so this is the first step. So where you can be a data contributor. So whenever anyone use your data, they will like use it for like any other purpose. You will get the rewards. So how that works? So first, let's go to the Explorer. So this is the LASI Explorer. So if we see, so this is my wallet address. So this is the transaction that happened. So we have, it's a token transfer transaction, which is none other than the DAT that I've received. The DAT is, as I mentioned, is a ERC1155. So this happens as a proof of ownership for the data I've provided. So whenever my data is being used, I will receive a reward, and then that is tracked through the same NFT again. So so that's the data contributor flow. And if you have like any questions, if we can answer that, else we can go to the next flow. So yeah, so this is the data contributor flow. Like you don't have to like utilize any other resources. You can just provide the data. And let's also look at the other flows where you can infer the data. It's not just being a data provider, but you also like infer the data you provide. So for that, I'll just use the uh, like a IDA address. So IDA is like it's where like the job is being handled. So I have one of the IDA address, and so for in order to check like the list of IDA, we can also use like different examples we have. So one of them I could show you is so we have like multiple examples related to inferencing. For example, this is for like providing data so it's like again a data contributors examples. So similarly, what we have done through like TypeScript, you can also do it through Python. But for inferencing, you can get so where you can get IDA addresses. We have like so client have different functions. So one of the client's function is so like active node list and then active node counts. So node counts basically provides you the number of nodes and active, and then so active node list will return you the active node list. So it's as a Python list type. So you can choose one of them. So currently we have only one, which is the IDAP, this address. So we you can what you can do is you can first check. So the get node function, again from the client class, what it does is it returns you with the URL and then more details on this particular node. And so what we are trying to achieve over here is, so we can able to provide data. So now we have to inference on the data being that we have provided. So we have here. So first we get the Lazy IDAV address and we create a client instance and we get the node details. And so we create we first like assign like the user who is using. So here the client dot wallet dot address, how this comes is like the client class is also exposed to the private key. So we also export our private key. So that's why like we are like not using any private key over here. So because the client class in that env, the private key is exposed, we don't have to like use it again. So from here, the client will retrieve the wallet address from the private key, and if the wallet address is exists, if the user is already exists, it will print is exists. Otherwise, it will add the user. So this is the cost, and then so this is where the deposit is happening. So if the user already existed, the user must have deposited. So that's why like if the user doesn't exist, uh, so the add user function will be called along with the cost. So this is in way, of course. This is not in ETH or anything. So this is way. And here, once that functionality is done, so here the deposit inference function happening. So here we deposit this amount of way. So this is like 10,000 like 100,000 way, not ETH way, to the large AI IDAV address in order to execute a certain job that we require. And then here we get the URL from the particular node, the large AI inference node, and we print it. And so this is where uh, the actual prompting happen, where you actually infer with the inference node. So with the URL you obtain, you can able to hit the API along with the Lazy IDAV address and the file ID. So we have provided a file ID here, which is 74. You can able to infer this if we pass the 74 over here. So this is what happens. We are not going to execute the inferencing line here, but like, apart from that, so let's see like how the URL looks like, and like how the try and accept blocks execute. So here you can see, so while it executed like the client inference node, so you can see that it have a inference address, and then the URL. So this is where this is the endpoint we hit in order to in order to prompt, in order to infer the data that we have provided. So that, and then so you can also see the public key of that node. So you can see the user is registered already, registered, and then the fee is deposited. In that case, we can go over here, as I'm using the same account in the both scenario. You can see the transaction that have happened when I executed this. So the last two transaction. First is the coin transfer, then this transaction. So the coin transfer transaction basically transfer the value of this much Laz AI to this address, and this is one of the handling accounts within the nodes. And here, in another, so this is the another transaction. Again, so this is again we only send like a message. So this is all happen when we try to like add user the first transaction, the coin transfer transaction. This is the second transaction that happened when the deposit inference is called. So this is how we can able to infer. So once we get the URL, we can able to hit the API. So far, like there are like few issues with this, but you can able to like you can able to call the LastAI address with the get node function to get the URL, and then you can able to hit it with the V1 endpoint along with these headers, and then to specify that whatever the file ID you have provided in the data contributor flow, you can able to use that to infer. So you provide your own data and then you can infer on that as well. So that is the goal. So everything remains private. So and then whenever your data is being used, your file ID is being used, you will also get the reward. So we have like several examples with different integrations where you can like build an agent with LastAI. You can also use like MCP servers, and then privacy, how you handle the privacy data, how you train the server. We have like several examples. So you can expect the demos on these examples on the following sessions, probably from the next workshop itself. We have workshops on every Thursday. And if you have like if you require like any particular workshop, you can also let us know through our forum or in the socials or in the Telegram group. We will definitely take that into consideration. So this is the major flow I wanted to show.
Awesome. Thank you, Theo, for the extensive overview on this. Yeah, our next.
Do we have any questions?
We don't.
Oh no.
Everything was perfectly clear. Um, but again, if anyone has any questions, feel free to reach out. We have a we're on all the socials, so yeah. From there, again, clarification for the HyperHack developers. You need to understand the overall architecture. You don't have to directly implement this, but just understand where it fits within your application. And so as a result, hopefully this video is a good reference for you guys. But again, if you have any further questions, feel free to reach out to me or Thiru.
Yep, anytime. And you can also join our Telegram group. I'll also drop the Telegram group here. Yep. So I've pasted the link. You can join, and then you can also like post your questions over here. Either like Pavel or me or like Nidhi, we will get back to you.
Yeah, perfect. Well, thank you everyone for showing up, and yeah, I guess we'll see you guys in the chats.
Yeah. Thank you, everyone. Thanks for had a really wonderful session, like explaining all the concepts of